Hello, we are COA and we would be presenting our project. Well, our system basically has inputs from devices namely D1, D2 and D3, and our focus is the device hub. Now the hub memory architecture looks like this, with buffers for each device, one for transmitting and one for receiving. We have designed a system with one M1 type of memory, four M2 types of memories, and six M3 types of memories. We have also considered two buffers for satellite communication, and we have the memory controller which controls the transmissions. These are the assumptions which we have considered. So all the megabits or megabytes are considered 10 raised to 6. We are designing our satellite communication system based on FAT system. We have implemented a transfer of command and data with Modbus protocol. For implementation of Modbus protocol, we have used colon as the identifier. We have d1.text, d2.text text files, which will be considered as a three device communicating with the hub. The hub sends ID 4 while retrieving or evicting data. Now this is the detailed structure of M1, where we have utilized the 256 KB in the following manner. The tag value and start address both combined have 3 bytes, and we have 64 columns. So we have 192 bytes. The next 4 bytes are considered for holding the next free location, which would be an integer data type. Then a 1 byte, which is a character data type, will be holding the next free index, while the 4 bytes in the integer data type would be determining the memory occupied. The rest 55 bytes will be used as buffer. We have done the following calculations for local communication. This is the cost of the device, which is $108. We have done this calculation according to the given values. Then the latency for sending and requesting from and by device to hub will be 5.5 megabits is the capacity. So 1 upon 5.5 mega will give you 181 nanoseconds. Now each clock cycle is of 10 nanoseconds, hence we have 18 clock cycles, and calculating for 1 byte will get 144 clock cycles. Hence for 1 byte latency in local communication is 144 clock cycles. Using 144 clock cycles, we have calculated the values for 128 bytes, 512 bytes and 1024 bytes respectively. Now the calculations for satellite communication are done accordingly. 1200 bytes per second, 1200 bits per second is the link capacity. So 1 upon 1200 would give you 8333333 nanoseconds and 833333 clock cycles. Thus it takes around 666664 clock cycles per byte. Additionally, satellite adds 100 clock cycles for uplink of 1 bit, hence 800 clock cycles for 1 byte. Now each byte sent to data center would need 667464 clock cycles. Command of 4 bytes would be going along with it, so that would be added in it, and it would give you 2669856 clock cycles. And the data center adds its own 50 clock cycles to carry out the data transfer. Hence the total would be 2669906, which would be the constant, plus 667464 into number of bytes. So these many clock cycles would be the latency. While if you are sending command from hub to data center and receiving data from the data center to hub, the calculations would be almost same, but the concept would be different. First we will be sending the command which is of 4 bytes to the data center. Data center will take 50 clock cycles to analyze the command, and then data center would be sending the data for downloading to the hub. So it would be the same clock cycles. For calculation of communication cost, we will be using the above calculated latencies. So basically the communication cost is $1 per minute. A single bit takes 1 upon 1200 into 100 into 10 raised to minus 9, so it would be 8.343 e minus 4. So transfer of 1028 bytes would need 6.86 seconds. So if we consider $1 for 3600 seconds, then for 6.86 seconds we would get $0.114. Now we have calculated the latencies and communication costs for the given test cases. So for test 1 case, we have 5.492 uh, 10 raised to 9. Communication cost is 0.912. For the second test case, we have 0 communication cost. And for the third test case, we have $1.14 as the communication cost. Now the command is of 4 bytes which we would be using. The first byte is colon, which identifies whether the command has started or not. The device ID gives the device which is transferring or requesting the data. Then tag values give the address. Data size determines whether it's 128, 256, 512 or 1024 bytes. Operation bit determines whether it's a send or request type, and LRC is the check bit which used for error checking. Now the data flow is according. Devices D1, D2, D3 send the data. That data is stored in the receiving buffers, then in the hub, and then that data is sent to the locations in one of the M2 or M3 memories. For our case, this data is stored in the text files of these devices. Now the M1 memory is used for indexing the tags so that location of data is obtained with least latency if any one of the 3 devices request data. So when a requested data is not in the hub memory, then again a data from one of the memory, that is M3, is evicted and requested data from the data center is obtained. Now if the hub is full and still the devices are sending the data, then the new data is directly sent to the data center. This is the multi-threading which we have implemented. So in this, D1, D2, D3 are in the form of text files which act as source of data. The program runs code for device 1, 2, 3 in parallel. This is implemented using threads in C language. The program uses the given CSV file extracts and its contents are used to operate D1, D2, D3 in the given order and in the given time. The output of the code is that it generates a D1R text and D3R text. So these are for request. The memory is filled in a sequential manner using 128 byte divider. When the data is full in memory, the remaining data would be sent directly to the satellite. Now we would be seeing how we have done our programming. So this is what we have got on our console panel. This is our code in the C program, and when we run the code we get these outputs which shows that that in the code execution of the code, you can see that there is LD1 counter, 2 counter and LD3 counter, which is representing the latency and the hub. There is also another counter as a global time counter which calculates the total latency required from sending the data from the local device and to the hub, and if necessary the data which is sent to the satellite and received from it. This whole latency is represented through a global time parameter, and this is how our system works. The output of the code which we have generated is in this format. So this is the original data format which you have sent
as a local device data, and this is the data which we have received back in the local device from a request command. This is the last request command issued by the D1 data. This is a similar case for the D3. This was the data issued by the D3 command, D3 memory register, and this is the result we have achieved, and it is stored in the d3r.txt file. These are the outputs of the code which you have executed. The D1 and the D3 are the source of the files as mentioned earlier. They are in the text format, and when the device requests data stored in the main memory, it is stored in the form of D1R, which represents the D1 request for read, and a D3R, which requests the read request from the D3 device. If you see, it's a difference in the data, and thus we have successfully designed a satellite hub device. Thank you.